Today we'll talk about fractional exponents, and you have not seen fractional exponents yet. Well, you actually have. Every time you see a radical sign, you actually are seeing a fractional exponent in a different form. We'll call this the power form or the exponent form, and on the right we'll see the radical form. So we just need to learn how to go back and forth from one form to the other. And it's a pretty simple thing to do. If you have a power like this on the left, you'll take everything except the denominator. Oh, that doesn't show. Everything except the denominator for something like this, and that will go underneath the radical sign. We're going to refer to that as the radicand. So I'll write x squared inside here. And then the bottom of the fraction, the bottom is called the index, but what you'll hear me say is the bottom goes in the pocket. So we'll just all we do is we take the base with the top of the fraction here, the numerator, and that becomes our radicand. The bottom of the fraction goes in the pocket. Simple thing to do. So on the one down below, we'll end up with y to the third as our radicand with a 5 in the pocket as our index. And it's as simple as doing that, going back and forth. But then what we'll do is we'll throw all the other laws of exponents on top of it, and we'll put all those things together. So let's look at some examples. We need to be able to go back and forth in both directions. Okay, so we'll start by changing some powers to radicals, and now we'll start applying some other things that we know and doing this all together. Well, I've got this term in here, raised to the 1/4. I'm going to take 2 times 8 and turn it into 16. So this is 16 to the 1/4. Now that I see that, whenever you see a fractional exponent, you can turn it into a radical. 16 to the first power would go underneath the radical, and the 4 would go inside the pocket. I wouldn't be finished here because I can still simplify the 4th root of 16. That's a number that will come out of your calculator, so there's my simplified answer. We want these answers in simplest form. Okay, in number 2, there are a couple of different ways I could go about doing this. I'm going to show you both ways. You'll have a lot of personal choice in this unit in terms of how you apply these exponents and the order you apply them in. Basically, it's going to be whatever occurs to you first. So I could first turn this into 2 with an invisible 1. I can leave that exponent invisible, put a 4 in the pocket, and multiply that times a radicand of 8 with a 4 in the pocket, also an invisible 1 for an exponent. When you see that expression, then you've got 2 radicals with the same index. We can take that into the 4th root of 16, and you'll notice now we've got the same thing we had in the first problem. Our answer is 2. Let's do this a different way. I can take these and turn them into, we had a little example like this on our papers yesterday. I could take 2 to the 4th and leave that the way it is. I could turn 8 into 2 to the 3rd. So basically I'm changing this base of 8 into 2 to the 3rd, still raising it to the 1/4 power, and now I can take care of adding exponents. First of all, 2 shortcuts going on here. 3 times 1/4 would give me 2 to the 3/4 on the right hand side. I'll bring that down. And then that's a multiplication between. This is 2 to the 1/4. What happens when you have the same base and you're multiplying? You can add your exponents. You leave the base of 2. When you add 1/4 plus 3/4, you get 4/4 or 1. So once again, the answer is 2. Now it just so happens that this problem and this problem turned out to be the exact same answer. That's because you could have also started this problem out by applying the 1/4 to that 2 and applying the 1/4 to that 8. So lots of different ways to do these, to start out either one of these problems. The last one on here, 25 to the minus 2/3. Well, yesterday we learned how to deal with negative exponents, so it's time to move that power so that it no longer has a negative exponent. Where do I move it to? I move it to the denominator. It becomes 1 over 125. Now it's a positive 2/3. I can change that denominator into a radical. It's 125 squared under the radicand, and it's a 3 in the pocket. If you pick up your calculator, that whole denominator will simplify to an integer. The answer is 1 over 25. So now we took fractional exponents, we turned them into radicals. Now let's go backwards. Let's take the radicals and turn them into fractional exponents. But again, we have to have simplified answers here, so we will make sure we don't have any negative exponents in the end. We'll start with this first one, the cube root of 12. it's 12 to the first power under that radicand, and the bottom came out of the pocket. So we're going backwards. So we'd write this as 12 to the 1/3 power, and that would be a sufficient answer. If you look at this one right here, again, a couple of different ways I can think of to do it. I'm actually I'm going to turn that in the parentheses. First, I will make that into a 9 to the 1/5 power. Pocket goes in the bottom. It's all being raised to the 4th. All I did was change what's in the parentheses, and now I can use my shortcut rule that says I'm supposed to multiply the 1/5 and the 4. That gives me 9 to the 4/5. It's got positive exponents, so we're good to go on that one. This one on the right, we always just bring down what we can't change. Get a little bit more room here. We'll bring down that 1/2. I'm going to start by splitting up numbers and variables. I think it's easier to work with if you do that rather than trying to do it all in your head at once. An a to the 6th and a b squared. Square root of 18, that has a perfect split for it. We'll bring down the 1/2, and the square root of 18 is going to become the square root of 9, square root of 2. This goes back to our radicals unit. Remember that when you are using perfect splits, then the first one will always become an integer, the second one will never change. If you recall, when we were working with radicals, invisible 2 in the pocket, 6 divided by 2 is 3, so the radical's all gone. 2 divided by 2 is 1, so the radical is all gone. Remember our assumption about invisible 2's in the pocket when we don't see any number in the pocket. Finish cleaning up. That's an integer 3, that's a 1/2. We multiply those, we get 3/2. Radical 2, there's really nothing you can do with the radical 2, but we're not allowed to have any radicals left in our answer, so we'll have to take that radical 2 and rewrite it as 2 to the 1/2 power. And this would be an a to the 3rd b. Now when you look at the end of this problem here, we've got a 2 on top of a fraction, 2 on bottom of a fraction, same base. So I'm just going to be working on these 2's for a little bit. We're just going to let the 3 and the a cubed and the b sit there for a while. Remember that when you have the same base and you're dividing, you can subtract exponents. So if I subtract these exponents, 1/2 minus 1 is going to give me a negative 1/2. I'm not quite done yet. It's 3 times 2 to the negative 1/2 times a cubed b. Got to keep going with this one. I can't use a negative 1/2, so I'll have to put that down the bottom. It's 1 over 2 to the 1/2 power, 3 times a cubed b, 3 over square root of 2 a cubed b. But remember our rules about rationalizing. That's got to come back up to the top. This would be a plain old 2 down the bottom. If you notice what we have here, you can go back up to the top and you can see that we actually had this answer here. But I just want to show you that you can still work with fractional exponents as long as you have the same base. But that's not a very good form. We're always going to take anything that's under radical goes at the end. So we're rearranging this. We're going to put the radical 2 at the end. We'll have the 3 and the a cubed and the b all out front. There's our simplified version. Last one we have up here, yeah, that is the last one on this page. Again, we're going to split up square root of 9, square root of a to the minus 2, square root of b to the 6th. And again, as you saw in this problem, you might think of this differently than someone else thinks of it. You can work with these differently. I'm not expecting everyone to have all exact same solutions and steps, but you should just follow all the rules to get to a simplified answer. You should all come up with the same simplified answer. Erase that. On this last one down here, square root of 9 will turn into a plain old 3. We've got a 2 in here. A negative 2 divided by 2 gives us a negative 1. Plain old 2 in here. 6 divided by 2, that divides evenly. Integer. The only thing we have to do is take care of this negative exponent right here. We'll write our answer as 3b cubed over a, and that's simplified. On the last page here, we'll be going, it's not the last page, is it? Yes, it is. On the last page here, we'll be going, this says to write as a radical expression in simplest form, so we want to put the radicals back in. This one is pretty straightforward. It's a radical 5 You can leave off the 1, we'll assume a 1 here, and you can leave off the 2, we'll assume the 2 here. So that would be your answer for 59. In 64, 6 to the 5th goes under the radical, and it's a square root. You can put the 2 in there or not. We'll assume it's in there if we don't see it. So you can pick up your calculator. That'll tell you it's irrational. You'd have to multiply out 6 to the 5th. You would discover that the biggest perfect square in 6 to the 5th is 36. So 36 would come out front, and it'll leave you a 6 under the radical, and that would be a simplified answer. And that's just playing around with the factors for a while. In number 65, we have a 5 to the 3 halves in the bottom of the fraction. We're going to turn that into a 5 cubed under the radical sign, a 2 in the pocket. Alright, so that's 1 over the square root of 125, but remember we have to rationalize denominators. So we're bringing the square root of 125 to the top, a plain old 125 on the bottom. Not quite finished. So you'll still have some reducing we can do here. Biggest perfect square in 125 is 25. And on the bottom we've got a 125. This will become a plain old 5. And I'm going to change colors here. So on top we've got 5 radical 5. On the bottom we've got 125. I can take a 5 out of the top. If I take a 5 out of the bottom, it becomes a plain old 25. So it looks like our answer is square root of 5 over 25. And then we'll start working with the variables here. We'll take a look at number 67 first, where we're going to split it up as 25 to the 1/2 times x squared to the 1/2 times y to the 1/2. And again, the methods that I'm choosing, there's nothing magic or definite about how you attack these. As long as you're applying rules properly, you might do things in a different order than I do. This becomes square root of 25, which we know is a plain old 5. This one, 2 times 1/2, is x to the 1st, which we know is a plain old x. This last one, y to the 1/2, is going to become square root of y, and that's already lined up so that it's a simplified answer. It's lined up properly. 69, oops, try that again. So number 69 is very much like number 67, so I think I'll skip and I'll show you number 71 here. That'll be the last one we'll do together. In number 70, well, we'll start on the top of this fraction. I think what I'll do is I will kind of distribute, quote unquote, that 7 first. X to the 5th to the 1/7. Remember, in monomials, that 1/7 will apply to every part of the monomial. Y to the 6th to the 1/7. And on the bottom I've got z to the -3/7. Well, I know I'm not going to have negative exponents here, so I'm going to move that z up top. And that's going to make it a positive 3/7. Now all my denominators are gone. We have to rewrite this as a radical, so x to the 5/7, y to the 6/7, and z to the 3/7 will become, and you might notice this right off the bat, but I'll show you the work anyway, 7 in the pocket, a 7 in the pocket, and a 7 in the pocket. This is x to the 5th under here. This is y to the 6th under here. This is z to the 3rd here. But we can only have one radical per term, so we'll make it all a 7th root, and underneath we've got an x to the 5th, y to the 6th, and a z to the 3rd.